the last part of the chapter we're going to do today. So first we're going to talk about the electromotive force. So we know that a force is a push or a pull, and this is the force that moves or pushes the electricity through a circuit. So we already learned before that potential difference is measured in volts, and a volt measures the electromotive force. And we learned yesterday that the unit of resistance is called an ohm, and again that's named after George Ohm. So we're going to continue with electric circuits. So a circuit, the path along which electrons can flow, that means the current. Because remember, current is the flow of electrons. And an electric circuit is closed if an electric current can move. So what that means is we have a device called a switch. And if I had a circuit like this, if it's open, there's not a clear path for it to take. So when it's closed, the switch, the current can keep flowing. So again, the best way to think about electricity is to think about current like water flowing through a pipe. So here it has a path that can continually flow. Here when it's open. So here if a switch is open, electric current cannot move through the circuit. And that makes sense. When we look at a light switch, that's what a light switch is. It's a switch. So when you turn the light on, you're actually closing the circuit and it can flow. When you put the switch the other way, it's going to be open. Today has to do with power. So power is the rate of energy consumption, and the unit is a watt. We studied power before, didn't we? But now we're talking about electrical power. So what we're going to see in physics is there's many different types of certain types of quantities. For example, we learned about forces. We keep learning about all different types of forces, but a force is a force, and a force is measured in newtons. Now we're learning about power. So before, when we learned about work and we learned about energy, we learned about power. Now we're learning about electrical power. So again, the unit would be the same, a watt. So the power rating of an electrical device, and we use electrical devices every day in our life, is found by multiplying the voltage by the current. This is the equation that's incorrect on the back of the homework sheet. So the correct is that electric power, P, is equal to the current I times V. The way I remember it, so this should just be IV, or I delta V. I always remember it as, for some reason, P is equal to VI. For some reason, back when I was in school, it means the same thing, but that's the way I always think about it. So this, you need to make that correction, and I'll show you in a minute on the back of the homework worksheet. So when you look at the equation, you can see that power varies directly with resistance. So power can either be I times V, or power can be I squared times R. And we'll talk about how we got all that in a second as far as deriving the units. So the total energy supplied to any device is the product of the power and the time, and a kilowatt hour is an energy unit. So again, it's the rate of energy use. Now, before we go on, let me just show you how these both are equal to power. So if we look at, so we said that P is equal to VI. So power is the voltage times the current. Well, we learned from Ohm's law that V is equal to IR. So if I take this information here and substitute it back in here, so instead of V, I'm going to write IR times I. Then I get P is equal to I squared times R. So you see how these are equivalent? Does everyone see that? Okay, so that's what I want to show you. That's why there's two equations for power. P is equal to VI. If I use Ohm's law and say V is equal to IR and substitute it back into here and substitute it, now I see the two different variations. Okay, so you could either derive this, or it might be easier just to remember it like this. That would be my recommendation. Okay. Now, what about power in terms of resistance? Well, if power is equal to I squared times R, and I know that I is equal to V over R, okay, so power would be equal to V over R squared. Now let me multiply this all out. So P is equal to V squared over R squared times R. This R cancels with that, so P is also equal to V squared over R. And I'm not even sure if that one's on the back of the review sheet. I don't think it is. So what you see is I have three different equations for power. So the first equation for power is in terms of V and I. The second equation for power is in terms of, so this is V and I. This one's in terms of I and R. And then this one, V squared over R, is in terms of V and R. So you see that the three equations for power, it all has to do with what I'm going to be given in my problem. Am I given the voltage and the current? Am I given the current and the resistance? Or am I given the voltage and the resistance? But these are all equivalent. Do you see how I used Ohm's law to derive the different variations? Okay. So it all depends on what you're given in a problem. Okay, so there's our three different variations for power. Now when we look at the next page of the notes, we see that when you pay an electric bill, you're paying for electric energy, not power. But we always call it like our, Florida Power and Light. So a kilowatt hour is equal to 3.6 times 10 to the 6 joules. We already learned that. And a lot of times when we look at power, we look at kilowatt hours. So let's look at some examples. A 6-volt battery delivers 5 amps of current to an electric motor connected across its terminals. A, what is the power rating of the motor? B, how much energy does the motor use in 5 minutes? So we're going to do just like we did before. We're going to write our given, we're going to write what we want to find, we're going to write our basic equation, and we're going to rearrange the equation to solve for the unknown in terms of the knowns. So when we read the problem, we're going to chunk it. A 6-volt battery. So right away I'm going to say that V is equal to 6 volts. Delivers 5 amps of current. Remember, if it didn't say current, you would know that amp measures current. What is the power rating? So I want to find P. So P is equal to VI, and a volt is a joule per coulomb, and an amp is a coulomb per second. And what happens is by writing the basic units, I can then carry my units through and cancel. This coulomb cancels with that, and I have 3 joules per second, and a joule per second is a watt. Part B, how much energy does the motor use in 5 minutes? So again, power is work divided by time. Work is equal to energy. Remember back when we did our whole unit on energy and conservation of energy, work is equal to the change in energy. So work is equal to PT, and 3 watts, and then I had to convert the minutes to seconds, and then I get the work done. The next example says a new color television draws 2 amps, so that's my current, when operated on 120 volts. A, how much power does the set use? If the set is operated for an average of 7 hours per day, what energy in kilowatt hours does it consume per month? And at 0.8 cents per kilowatt hour, what does it cost of operating it for a month? Okay, so I'm given my current, the voltage, and the time. Again, I need to convert my time to my basic, which is seconds. So for the first part, I'm going to say P is equal to VI. And I have 120 volts times 2 amps, and that gives me the power in watts. Then when it says the energy, so remember, work is equal to the change in energy. So when they say what is the energy, I'm finding the work. So work is equal to PT. And then the last part says the cost. So because they tell me how much it is per kilowatt hour, again, I don't recommend writing your units like this. If I had a kilowatt hour, and then if it's by itself, put it in the numerator. And then over here, when I have the cost in dollars per kilowatt hour, when I clearly write my units with the numerator and the denominator, it's easy to cancel. This is kind of like yesterday when we were doing the number of electrons, and you had to know the charge on one electron was negative 1.6 times 10 to the negative 19 coulombs. So when you clearly write your units in numerator and denominator, it's very easy to cancel. Now the last part of the notes, first it has a table. This is to help you with the whole chapter. Some of these units we've done before, but we have what something's called, what the symbol is, what the unit is, and then the unit symbol. Because when you're not sure what something is, if you know that resistance is measured in ohms or charge is measured in coulombs, it's going to help you to identify. Now, in the notes, there's not a mistake. You see in the back of the notes, it has the correct equation for power. Okay? So the notes is correct. It's just on the other homework sheet, which we'll do in a second. And that's it.